I slept in this morning. We normally leave my house at 7, and we didn't leave my house until 7:20. And there's a whole lot of yelling going on to get my children to leave at 7:20. So it's very stressful. And I made muffins, and it was ridiculous. Okay, so we've talked about the fundamental theorem of calculus part 1, but we're going to talk about it a little bit more today, and we're going to talk about how we can actually do stuff with it, because we kind of looked at it on that packet, but we haven't actually done anything with it. A triumph of mathematical discovery. And so look, I didn't even make you write anything here, but again, I copied some stuff from the book for you. Oh, look, you were supposed to write this, but I didn't even do that. Oh, I failed. We did this on the little packet that I had you do, the discovery. We discovered that if you have the integral from a to x of some function, right, that if you take the derivative of that function, the derivative of the integral, then you just get back the function f of x. That's what we did over and over again on that packet of, we made the connection of, oh, that's just the derivative graph. And it seems like, oh, okay, derivatives and integrals are inverses of each other. They kind of undo each other. And it's easy to think, okay, what's the big deal? But your book tells you it's a really big deal. It's difficult to overestimate the power of this equation. It says, if this is true, every continuous function, I'm going to underline all this important stuff, every continuous function f is the derivative of some other function, namely the integral of a to x of f of t d of t. It says that every continuous function has an antiderivative, and it says that the processes of integration and differentiation are inverses of one another. So that one little equation there tells us that, and I love your book. It says, if any equation deserves to be called the fundamental theorem of calculus, this is surely the one. That's some good writing there, right? I've never enjoyed reading a math book, and until this book, it's my favorite.
I was reading a book about this mathematician guy who was just like solving problems, but he had a weird life. And then literally like the first fourth of the book was like 40 years of his life. And I'm like, what is the rest of the book gonna be about? I don't understand. And I just
I had to take it back to the library. Okay, so basically, if I ask you to take the derivative of an integral, usually there's an x up there, right? And so one, you have to remember that this means derivative, right? So if I want to take the derivative of this integral, remember that they're inverses. So it's like the derivative cancels out the integral, but you have to plug the x into the problem, right? So let's go back and look at that one more time. When you take the derivative of the integral from some number to x, you get f of x, so the x goes into the problem. But we're not taking antiderivative right now. It's like these parts cancel out, right? You with me on that? So if I take the derivative of this, dy dx, from 0 to x, I'm just going to plug x into that problem. And I get the sine squared of x. But it can't always be that easy, right? Like, it's calculus. So you have to look for things. What are they going to change on you? So look at number 2. What's different about number 2 from number 1? The x is the lower bound and not the upper bound, and that's not okay. The fundamental theorem of calculus says it's a to x. So I want to switch it. So can I do that? Can I move the x to the top and the 6 to the bottom? But what do I have to do? I have to use that property and make it negative. And you're probably not going to write all this down because I know you. What is that noise? What is he doing? I don't even have my door locked because I'm waiting for Jared to come in. We all get shot. It's Jared's fault. It's your fault, Jared. Yesterday, my Algebra 2 kid said, why do you even lock your door? No one else locks their door but you. And I was like, well, when everyone gets shot, I'll be the only one alive. And they're like, it's not true. They'll just shoot the door handle. And I I said, no, there's video of like shooters in a school, and they go through, and if the door's locked, they move on because they don't want to waste time. They know the police are on their way, so they don't waste time with locked doors because they know they're gonna find an unlocked door. I was like, so that they're gonna, my door's gonna be locked, they're gonna go to the next door. And my whole Algebra 2 class were like, not Miss Bye. I was like, you don't even care, like you just want me to get shot because you just want to save Miss Bye. And I'm like, no, Miss Vi locks her door now too because I told her she doesn't want that I'm locking mine, so she doesn't want to get shot too. It's got to be really funny to watch my videos at home when I just like go and talk randomly about 12 fingers and such. Is that right? I just put the negative and I just changed the T to X. Right? So you just got to remember if the bounds are changed negative. That's still pretty easy, right? What else can I do? Oh, look at these. What do you think about this? This is what you're going to see on your AP test. 1 and 2, that's like baby calculus. They're not going to put that on the AP test. That's too easy. They're going to put this on the AP test. So we definitely still have to plug it in. So we have a number to x squared, but now we have this x squared up here. We're taking the derivative, so I'm still going to just plug that in. So I get cosine of, I'm going to put this in parentheses, of x squared. But I kind of have to do like the chain rule. Oh, remember the chain rule? So when it's just x, what's the derivative of x? 1. So that's why we don't have to think about it if it's just x. But if there's some function up here, you have to multiply by the derivative of that function because you're taking the derivative of the whole thing. So you have to multiply by the derivative of x squared, which means you have to put a 2x out here because you're taking the derivative. You could do the same thing when it's x up there, but the derivative of x is 1, so that's why they don't write it out that you need to multiply by that. You could leave this like this, but I don't like it. So I'm going to change it to 2x cosine of x squared. And I guess, I don't know if that needs to be in parentheses. It doesn't really need to be in parentheses, but just know the squared is with x, right? Not with cosine. But if you wrote this, I can't mark that wrong. I just think it looks ugly. Okay, now putting it all together. Do number 4. The bounds are mixed up, and there's a function. Ready, go. Talk to your table. Sabrina has to talk to herself. I crack myself up sometimes. You can move back with the clothes in matter if you want, or you can just deal with it. We're gonna get done with these notes way too early, just so you're aware. Who rides a motorcycle to school? In the rain. There's like a purple and pink motorcycle out there. Is that Colin?
Colin McAllister, Cody Wyatt, and who was the other? Hunter Higgins, McAllister, they all have motorcycles. You wouldn't surprise me if it's Collins. What? So it would just be X, right?
Tyler and Lois are the only two that talk to each other. Oh, kids. Should need a negative, yes? And then we're plugging the square root of x in here, but then we're squaring it. And then we're multiplying by the square root of x, which remember is x to the 1/2. So that would be like 1/2 x to the negative 1/2. Right? So here's what's fun about this is like, well, not right now, but like when we do, like we just did antiderivatives where we're going backwards and we're adding one, but then we're doing derivatives here where we have to subtract one, so your brain has to work really hard. Am I adding or am I subtracting exponents, right? We're derivatives here, so we're subtracting. And then you can just kind of clean it up. I would say that that's negative sine and the square root of x squared. Can I just say that's sine of x? Yeah. Should I say... trying to decide if I should put absolute value bars around it. What do you think? Because if it's x squared, do you agree that's going to always be positive? 1. Also, square root of x, you can't take the square root of a negative number. That's kind of iffy, but I think I would put a square root. I mean, absolute value bars around it. Just saying. Because what if they gave you a negative number there? I don't know. I'm overthinking it. But I definitely think you should simplify that. I don't know if I should do this or not. I'm unsure. How do you feel about that? Okay, I got one other thing, and I refer you to a book example. It says, construct a function of the form y equals integral from a to x of f of t dc plus c that satisfies the given conditions. And so now they're kind of giving you to work backwards. They're giving you a derivative, and they're giving you a point. They're telling you that y equals 0 when x equals 8. And they want you to construct the integral that satisfies that situation. How do we know what the bounds are? Can I put the top bound as x? Hopefully. Which kind of works. You see how there's an x over here, so it seems like nothing crazy is going on there. Then I could put an x up there. What do you think the bottom bound is going to be? I'm guessing it's one of these two numbers. Which one would you guess it is? The y value or the x value? Because aren't my bounds like on the x-axis, my bounds? So this is your bottom number there. And remember that that a value can change, and if you go back to that discovery thing that we did last week, like what happened when the bottom number changed, it was just a transformation, right? It just moved the graph up or down. So that number is your bottom bound. And then think about what we're doing on these. As long as there's nothing tricky with the bounds changing or a function like something other than x, isn't this what my original integrand is here, right? Like I'm just going to change these x's to some other letter. It says t up here. So could I say e to the t tangent of t? dt? Then we have this plus c, right? And remember that you always can have this constant out here. And that's where the y value comes into play. All right, like that's telling you, like on this one, y is 0 when x is 8, so we're just on the x-axis. But if y was some other number, that means that we're going to be moving. So on this one, I'm going to put a plus 0 here. That's your c value. And I want to encourage you to look at example 4 in your book, because they do one when it's not a y equals 0, and they kind of explain it all, and I think that it's worthwhile to look at. We'll do some more stuff with that later. But for now, if y is 0, you don't have to worry about some number added out here. But if y was something else, like if that was y equals 3, we would have to put a plus 3 out. Okay?
So any number y is just added.
And again, example 4 in your book talks about that a little bit more. So I just want you to do 3 through 24 multiples of 3 on this, and then we will do 5 for day 2 tomorrow, which is Fundamental Theorem of Calculus Part 2, which really isn't that new because we've been doing it already, but we're just going to call it that tomorrow. Officially.